Welcome to the data science training, causal reasoning. And my name is Walter Leite, and I will talk to you about propensity score analysis. Propensity score analysis is a method used to estimate treatment effects when there is no random assigned to condition, so when it's not an experimental study, but there is a rich set of covariates that can be controlled for. It is a very popular method because it allows controlling for a large number of covariates. It's based on the propensity score, which is the conditional probability of treatment assignment. The propensity score can be estimated with any method that can predict the probability of treatment assignment. So the propensity score is estimated with both parametric or non-parametric methods, including machine learning. So it's very powerful because Rosenbaum and Rubin showed that if you balance the treatment and control groups with respect to propensity scores, you also achieve balance with respect to all covariates that were used to create the propensity score. So assuming the propensity score was estimated correctly. Therefore, it's a powerful data reduction technique. If you could have 80 covariates, and then if you estimate the propensity score as the predicted probability of treatment assignment based on these covariates, you can just adjust on the propensity score, which means you'll be balancing all the 80 covariates. So the property of the propensity score is to try to achieve strong ignorability of treatment assignment. This means that if the potential outcomes are independent of treatment assignment given covariates, they also be independent of treatment assignment given the propensity scores. So propensity scores allow you to use smaller models because it doesn't really matter if you have 30 covariates or 50 covariates or 80 covariates used to estimate propensity scores. Once you balance treatment control groups with respect to propensity scores, you can set those covariates aside and estimate the average treatment effect or any treatment effect of interest without them. You will not need to include the covariates in the outcome model. Therefore, you don't need to make any linearity assumption between the covariates and the outcome. You don't need to model the functional form of the relationship between covariates and outcome at all. So propensity scores analysis is a multiple step method. There are 6 steps, starting with data preparation. You estimate propensity scores, you implement the propensity score method, which would be matching, weighting, or stratification. Those are the most common. Then you evaluate covariate balance between treatment and control group. This step is your measure of success of removing selection bias. Then you estimate your treatment effect of interest and perform a sensitivity analysis to understand the robustness of your control for selection bias. So in the data preparation step, you have to select covariates, and then you have to handle missing data, which it's very common for a large number of covariates to have missing data. For example, let's say you are interested in estimating the effect of working for a company that provides or subsidizes childcare, or the length that working mothers breastfeed their children. This example can use data from the National Longitudinal Survey of the Earth 1979 and the NLSY 79 Children in Earth. So for this example, we have 107 mothers that worked on for a company that subsidized childcare or provided, which is 8.85%. That's pretty typical of propensity score analysis, where the treatment group is much smaller than the control group. The variables that you want to control are in gray here. The most important are true confounders. So true confounders have a relationship with the treatment assignment mechanism and the outcome, and omitting true confounders leads to biased treatment effect estimates. You also want to control predictors of the outcome, because even though omitting them does not lead to bias, including them increases your power, because it reduces variance, right? So what you don't want to include are variables that are just related to treatment assignment but not the outcome, because including them will increase variance or reduce power. So the main message is include true confounders, predictors of the outcome, but not predictors only of treatment assignment. In practice, it's difficult to differentiate between these three, so most researchers use a more expensive approach where a very large number of covariates are included, because it's better to have more control of bias than to potentially be more efficient for a bias estimate. So these are strategies usually employed to identify covariates that need to be included. So look at theoretical analysis for which factors influence adoption of treatment or selection into treatment. Sometimes it's possible to do pilot studies, expert reviews, interviews with individuals that understand the reasons why participants sign up for the treatment or participants are placed in the treatment. And you can do exploratory analysis also with subsample of data. Typically, the most important covariate to include is either a pretest of the outcome, like a previous measure of the outcome, or a proxy of the outcome. So, for example, if your outcome is algebra achievement, but you have a previous measure of mathematics achievement, that will be a good covariate to include, because its mathematics achievement is very related to algebra achievement. So for the example, using the National Longitudinal Survey of the Earth, 31 covariates were selected that include benefits provided by the current job, education of the mother, which influences the job they will receive, work hours worked per week, employment sector, family size, type of birth, and so on. So there could be a lot of missing data. There are different methods to handle missing data, a large number of methods. List-wise deletion is usually not recommended, because unless the data is missing completely at random and the proportion of missing data is small, it will result in selection bias or in bias due to the missing data. Single imputation can be acceptable, it can provide adequate results, especially if the proportion of missing data is not very large. Let's say 20% or so at the most. For list-wise deletion, I would say less than 5% of missing data. And multiple imputation would be the gold standard here. There are many ways to perform multiple imputation. There is the two main approaches is joint modeling and conditional specification. Conditional specification is also known as MICE, multivariate imputation by chain equations. That's my preferred method. I put a citation here for a paper that provides a more thorough discussion of this. Once you have selected the covariates and handled missing data, you are ready for the next step, which is estimating propensity scores. So, among statistical models, any model to predict a binary outcome are very popular. So, logistic regression by far is the most popular method to estimate propensity scores. Now, among machine learning methods, classification trees, boosting, bagging, random forests, any supervised learning method like any classifier would work. The most common is generalized boosted modeling, and that's because there is a package in R called Twang that it makes it very available, like easily available. So, which made it the most popular method. So these are some of the packages you can use, functions. GLM for logistic regression, GLMER, Survey GLM, Ranger for random forests, and Twang for generalized boosted modeling. Once you estimate propensity scores, it's important to understand the common support, which is the area of the propensity score distribution that overlaps for both treatment and control. There needs to be adequate overlap. Now, this is typically a visual inspection, but the degree that common support needs to be strong depends on the propensity score method used. So, for example, one-to-one matching requires a lot stronger common support than propensity score weighting. So the visual inspection is just to understand more serious problems, but you have a better view after you implement your propensity score method. Now, what if the overlap is terrible? So this would indicate that the groups are too heterogeneous. So in other words, the treatment group is very different from the control group, as comparing apples and oranges. Therefore, propensity score analysis wouldn't be appropriate. Now, if imbalance is not too severe, but it could be improved by adding by additional covariate adjustment in the outcome model. You could improve by changing the method to estimate propensity scores as well. So the next step is propensity score implementation. The most common methods are weighting, stratification, and matching. And I'll talk about a little bit about each of them. So weighting is to create weights that balance the treatment and control group with respect to covariates. In other words, the weights adjust the distributions of covariates so they are similar across treatment and control groups. Weighting in propensity score analysis is similar to weighting in survey methods, and the form of the weight depends on which quantity you want to estimate. The weight to estimate the average treatment effect is commonly known as inverse probability of treatment weight, IPTW. And as you can see in the formula, for those treated is 1 over the propensity score, and for the untreated is 1 over 1 minus the propensity score. Okay, so it's the inverse of the probability of receiving the condition the individual received. Now, for estimated average treatment effect on the treated, treated individuals receive a weight of 1. Untreated individuals receive a weight that's equal to the odds of treatment, so it's the propensity score divided by 1 minus the propensity score. So for estimating the ATT, weighting is sometimes referred to as weighting by the odds, because you weight the untreated by the odds of the treatment. Propensity score stratification is can also be used. It doesn't reduce selection bias as much as weighting, because the strata are less precise. The most common number of strata used in applied research is 5. So stratification can be seen as a less precise form of weighting, but it does have an advantage that it's more robust to model misspecification. So if the model is somewhat misspecified, it could affect creating weights, but maybe not affect the strata membership. So for propensity score stratification, you have two approaches. One is to estimate the treatment effects within strata, and they combine the treatment effects across the strata. Or the second option is create marginal mean weights across the strata. That's my favorite approach when I use stratification, because these weights can be treated the same way you treat weights for propensity score weighting. Matching is used in a different forms. The most common is one-to-one matching. So matching can be classified into a replacement, either it has replacement or not, an algorithm, and a ratio. Replacement, there are two variations: matching with replacement, matching without replacement. Matching with replacement is more precise. Matching, but with large sample sizes, there is little difference between with and without replacement. Algorithms, some algorithms perform better. Greedy is the simplest algorithm, which is just for each treated unit, find the closest untreated unit in terms of propensity score without considering the overall balance of the distributions. So without considering the other units. And that is the most common, but also the simplest form of matching. Optimal matching and genetic matching are more complex. Genetic matching tries to minimize the distance between covariates, so it optimizes on covariate balance. And you can also match one-to-one, so each treated observation is matched to one untreated observation. You can do 1 to a fixed number, so 1 to 3 or 1 to 4. Variable ratio matching, which is every treated unit is matched to as many available good untreated units. And the full match tries to match every unit. The only one here that I wouldn't recommend is 1 to k matching, because, for example, let's say you fix that you match each treated unit to 5 untreated units. There may not be 5 good untreated units, there may just be 2. So you're sacrificing quality by forcing the match to 5. But all the other methods work. Now, they all generate weights except for one-to-one matching. And therefore, in terms of analysis, it becomes similar to propensity score weighting, because you have to account for the weights. The one difference, though, between weighting and matching is that for most matching methods, you end up with a smaller sample size because you drop some units, but for weighting, you have the entire sample size. The exception is full matching, which preserves your entire sample size. Full matching can be thought as a more precise form of stratification. Now, usually matching is done on the logit of the propensity score, so it's the log odds of the probability of treatment. It's log of the odds of treatment instead of the probability of treatment itself. So for propensity score implementation, Matchit is a popular package for matching. There is also matching, which focuses on genetic matching. Twang is a great package for weighting. It automates a lot of weighting especially if you're using generalized boosted modeling for estimating propensity scores. And then weighted can estimate propensity scores in a variety of methods and provide weights. After you implement the propensity score method, weighting, stratification, or matching, it's time to evaluate the success of that procedure. And this is done with evaluation of covariate balance. So it consists of comparing the distribution of treatment and control for each covariate. The most common method is just based on difference between means, standardized difference between treatment and control on each covariate. So visual inspection can be used, such as histograms, Canada density estimates, QQ plots. Descriptive criteria, which standardized mean difference is by far the most common. So you can calculate that standardized mean difference in different ways. You can use the difference divided by the pooled standard deviation, or you can use a lot of software use the standardization just with the standard deviation of the treatment group. Now, in terms of criteria for adequate covariate balance, it's a bit field specific. Peter Oste is in the health sciences, and he advocates for 0.1, and that's commonly used in the health sciences. In education, the What Works Clearinghouse guidelines define baseline equivalence as differences between covariates being less than 0.05 standard deviations. However, the What Works Clearinghouse use two criteria. So if you achieve a balance of 0.05 standard deviations, you do not need to include the covariates in the outcome model. However, for covariates that have balance between 0.05 and 0.25, it's still acceptable as long as you include those covariates in the outcome model. And then more than 0.25 standard deviations, then it's not acceptable. There is no baseline equivalence. For checking covariate balance, the Cobalt package is excellent, can accommodate a lot of methods. The Twang package focuses on weighting. So I have here an example of output from the Cobalt package, and you can see these are standardized mean differences. They're all very small. They are all less than 0.1, mostly less than 0.05 in absolute value, except these two here. So the appropriateness here would depend on which criteria you're using. Now, this is how a typical covariate balance table is published in a paper. In every application of propensity score analysis, it is essential to provide a covariate balance table. So here, a common way to do it is provide the standardized effect sizes before and after implementation of the propensity score. So here we have a baseline standardized mean differences, which shows the difference before using propensity score weighting, and then the differences after propensity score weighting. Note that they are much smaller. Not all of them are smaller, but in general they are smaller, showing that there is an improvement in covariate balance. And this is the paper where this example partial table comes from. Now, if you do not achieve adequate covariate balance, one option is try to, if it's just a few covariates, you can add them to the outcome model, but you can also try changing the propensity score estimation method. There are once you achieve adequate covariate balance, the next step is to estimate the treatment effect. There are a variety of ways of estimating. There are broadly model-based estimators and design-based estimators. So regression is a type of model-based estimator, where here you have a very simple model with the outcome and the treatment indicator as the only predictor. You could add covariates to this model. You could use any generalized linear model to estimate the average treatment effect. You could use a mixed effects model. So model-based estimation allows any type of model. Design-based estimators they don't make the same assumptions as parametric models. So, for example, the Horowitz-Thompson estimator for weighting is just the difference between weighted means of the outcome for treatment and control groups. There is the Abadie and Imbens estimator for matching, which is based on the idea that the matched units are providing the potential outcomes. So it's the difference between is the mean of the difference between potential outcomes that were obtained through matching. There are several packages can be used for estimating. Now, because most propensity score methods generate weights, the survey package is extremely useful for this, and it can estimate, do model-based estimators with a function like survey mean or survey contrast, or it can implement model-based estimation too with a function like SVY-GLM. The matching package implements the Abadie and Imbens estimator. And here is an example from the matching package, provides an estimator, a standard error, p-value, and you can do additional adjustment for covariates. After you estimate the average treatment effect, it is critical to do a sensitivity analysis. Sensitivity analysis is the last step of propensity score analysis. It asks the question of whether the conclusion would change if you had omitted an important covariate. Remember, the propensity score analysis only controls for observed covariates, so it's important to understand the impact of omitted covariates. The packages to do that include SenseMaker and Confound. Here is an example with Confound. This at the top you have the output. So, for example, it's showing that for to sustain the inference of that example, which the inference is that there is no significant treatment effect, 27.7% of the estimate will have to do to bias. So that is a good chunk. So it's not very sensitive. And you'd have to switch 57 cases. So with matching, the sample size was 196, so 57 is about 25% of the sample size to be able to sustain that inference. So this is the reference for the method. And here there are some additional readings. My book, Practical Propensity Score Methods Using R, has extensive treatment of propensity score weighting, matching, stratification, as well as propensity score methods for multiple treatments and continuous treatments. And also recommending a paper that shows how to do propensity score methods with latent variables, and a paper that shows how to do propensity score methods with multi-level data.